to tutorial 17, which is the 8th tutorial we've had on Core 3 Trigonometry. Let's take a look at the syllabus. Edexcel says we need to know the following. We've covered everything in green, and in the last tutorial we talked about the addition formulae: sine A plus B, sine A plus or minus B, cos A plus or minus B, and tan A plus or minus B. Now we're going to focus in on the thing that these addition formulae lead to, and they're the double angle formulae. So I'm going to introduce you to that today. Okay, let's start by reminding ourselves of the addition trigonometric formulae. These are what we learned in our last lesson. Now, from these we get very easily the double angle trigonometric formulae, and by that I mean we get an expression for sine of 2a, cos of 2a, tan of 2a. Okay, so sine of double an angle, cos of double an angle, and tan of double an angle. And the way you get them for each of these would be as follows. Sine of 2a is the same thing as sine of a plus a. Now, we could expand sine of a plus a using the addition formulae, where we could think of b being equal to a. So we could say, using this addition formulae here, it would be sine a cos a plus cos a sine a. Okay? Well, of course, sine a cos a is the same as cos a sine a, so this is simply 2 sine a cos a. And this here is what's called the double angle formula for sine 2a. So sine of 2a is equal to 2 sine a cos a. Now, that works in many ways. For example, sine of 4a would be 2 sine of 2a cos 2a. Okay, this angle has to be double these angles. That's the only requirement. So that is an example of a double angle trigonometric formula. I advise you to try and work out an expression for cos 2a and tan 2a on your own. Just see if you could do that on a piece of paper, just doing the same thing I did with sine 2a. And in the next slide I'll show you what those are anyway. So just take a moment, see if you can find those, pause the video. In a moment I'll show you what those turn out to be. Okay, so these are what turns out to be the double angle formulae. Sine of 2a is 2 sine a cos a, cos of 2a is cos squared a minus sine squared a, and tan of 2a turns out to be 2 tan a, all divided by 1 minus tan squared a. And they are our double angle trigonometric formulae, all taken from the addition trigonometric formulae, making the second angle b in those equal to a. Now, there's one further extension we can go, and we get an extra pair of identities with cos 2a. This has a cos squared and a sine squared, and we can use the fact, let's say on the one hand here, that sine squared a, using our core 2 identity, is 1 minus cos squared a. And instead of having sine squared a in here, we could substitute 1 minus cos squared a, and we would get that cos 2a would be equal to 2 cos squared a minus 1. And on the other hand, if we instead substituted for cos squared a, because we know cos squared a is 1 minus sine squared a, then if we substituted 1 minus sine squared in instead of cos squared a, we would get the identity cos 2a is equal to 1 minus 2 sine squared a. Okay, so a simple replacement of cos squared a by 1 minus sine squared gets us a new identity, or a replacement of sine squared a as 1 minus cos squared a gets us another one. And just to tidy these up here, if I rob those out here, rob that out here, okay, nice and neatly, these are two further extensions or different identities for cos 2a. Cos 2a can also therefore be written as 2 cos squared single a minus 1, or cos 2a can be 1 minus 2 sine squared single a. And these 5 identities here we need to be able to use, and more than that, we need to be able to derive them. These are not given in the formula booklets, but they are a simple derivation from the addition formulae, which we do have. So the rest of the video is going to be using these to do various trigonometric equations, identities, etc. So let's start off with an example. We're going to use the double angle formulae to find exact trig values. And I've written the three main ones here, but remember there are two extensions for cos 2a. We are told that cos of x is 3/4 and that x is between 180 and 360. We are told to find the exact value of sine of 2x. Well, let's just follow our nose. Sine 2x by the double angle formulae is 2 sine x cos x. Now luckily we are given cos x already. We know the value of cos x. We do not, however, know the value of sine x, so we better find the value of sine of single x. Now we know this is a separate bit of working over here. This is a separate bit of working. We know that sine squared of x must be 1 minus cos squared of x. So sine squared of x must be equal to 1 subtract 3/4 squared. Okay, and so sine squared of x must be equal to 1 subtract 9 over 16, which would be 7 over 16. Now, what is sine of x then? Well, we take square roots of both sides, so it will be plus or minus the square root of 7 over 4. Now the question is, which one is it? Is it the plus square root of 7 over 4, positive square root of 7 over 4, or negative square root of 7 over 4? Well, let's draw a quick graph for sine, and we're going to draw a graph as so. Now, we know we're looking between 180 and 360. We're looking for this portion of the graph, and we know that this portion of the graph sine's negative. So we only care about the negative value for sine x. Okay? So now we've got an answer for sine x. We are given cos x, and now we can go on and work out sine 2x. So sine 2x is therefore 2, and we've worked out that sine x is negative root 7 over 4, and we're told that cos x is 3 over 4. So we need to multiply these out, so we get 2, and we get negative 3 root 7 over 16, and timesing that out, we would end up getting negative 3 root 7 over 8. And we have an answer for sine 2x. As follows. Okay? And we're done on that. Now, it then asks us what tan 2x is. Okay? It asks us what tan 2x. Well, this is going to be slightly easier, hopefully. Tan 2x, using our identity, is 2 tan x over 1 minus tan squared x. And a little bit of separate working. We don't know what tan x is currently, but we know that tan x is equal to sine x over cos x. Okay, sine x over cos x, which in this case would be equal to, well, we know sine x is negative root 7 over 4 divided by cos x, which is 3 over 4. So we would get that as negative root 7 over 3. And so substituting in here, we would therefore get this is equal to negative 2 root 7 over 3, okay, divided by 1 minus this squared, which would be 7 over 9. And I'm running out of space here, but this is negative 2 root 7 over 3 divided by, well, 1 take away 7 over 9 is actually 2 over 9. Okay, and this is like dividing by 2/9, it's like timesing by 9 over 2. So this is the same as negative 2 root 7 over 3 multiplied by 9 over 2. The 2's would cancel, and the 3 there would cancel with the 3 there, and we should get negative 3 root 7. So negative 3 root 7. And we're done. I'd encourage you to have a go at the next example. It's very similar in style. Have a go, pause the video, and I'll show you the answer in 10 seconds. Okay, we want cos 2a, so cos 2a using our double angle formulae is simply cos squared a minus sine squared a. Okay, now we've got cos squared a, we could find sine squared a, and then we would substitute those values in and find what cos 2a is. But we could be a bit cleverer here, and we could say that we know that sine squared a is 1 minus cos squared a. So actually this is simply 2 cos squared a take away 1 if I substitute that in here instead. So we would have an answer 2 negative a third squared take away 1. Well, that would therefore be 2 ninths take away 1, and the answer would be negative 7 over 9. Okay, now let's move on to a different type of question. We're proving the identities here. It tells us if we expand this, it must be using our addition formulae. We want to show that sine 3a is equal to this here. So expanding this, I think we need to use our addition formulae. So we say that sine 2a plus a. Using our addition formulae here, that must be sine 2a cos a plus cos 2a sine a. Okay, now we know an expression for this using our double angle formulae, and we also know an expression for this using our double angle formulae. Now the thing to bear in mind here is in the final answer we just want sines, we don't want coses, so that will be something to bear in mind here. On that note then, let's substitute in here for sine 2a. That would be 2 sine a cos a, and we still have this cos a here, cos a. Now this here, because we want only sines and sine squares and cubes in our final answer, instead of substituting cos squared minus sine squared a, we're going to substitute instead in for that just cos 2a in terms of sines. Okay, so we're going to substitute in there 1 minus 2 sine squared a for cos 2a, and we'll have our sine a here. Now it's time to expand out, so all the same colour pen here, we would use 2 sine a, and we've got cos squared a here. This times this would give me cos squared a, and then here we would have plus sine a minus 2 sine cubed of a. Now we're looking fairly good. The only thing that's causing us a bit of issues is this here. We don't want cos squareds in our final answer, we want all in terms of sines. So we're going to substitute this for 1 minus sine squared. So this would be 2 sine a, 1 minus sine squared a, plus sine a minus 2 sine cubed a. Okay, we're going to expand this out then. This would be 2 sine a minus 2 sine cubed a plus sine a minus 2 sine cubed a. And now we are virtually there because 2 sine a plus this sine a gives us the 3 sine a we're after. So we get 3 sine a. And the negative 2 sine cubed, subtract another 2 sine cubed, gives us the negative 4 sine cubed a we're after. And hence we have shown that sine 3a is what we were asked to show, and we're done. Okay, time for you to try one yourself. I've given you identity with tans in it. Have a go at this, pause the video, check your answer in 10 seconds. Okay, going through this, our only option is to start with the, let's say, the left-hand side, and to write out what tan 2 theta is. Tan 2 theta is 2 tan theta over 1 minus tan squared theta. Now we want to make it look like this. We want a 2 on top, we don't want 2 tan theta on top. So if we divided both top and bottom by tan theta, what would we get? Well, we get the 2 on the top, we get 1 over tan theta here, and we get minus tan squared over tan theta here. And that would simplify to what we're looking for. 2 over 1 over tan theta is cot theta, that's what we wanted, and tan squared over tan is tan theta. And we have proved that it's equal to the right hand side, and we're done. Okay, and next thing we need to be able to do, we need to be able to solve equations using the double angle trigonometric formulae. So here's an example here. We're asked to solve 3 cos 2x minus sin x, 3 cos 2x minus cos x plus 2 is 0 between 0 and 360. Now we can't currently solve this because we've got cos of a double angle and cos of a single angle going on. So we need to make it all in terms of a single angle. So we know that cos 2x would be cos squared minus sin squared. But let's get everything in terms of cos 2x, cos x's. Let's use the substitution that cos 2x is 2 cos squared x subtract 1. That's a version of this. Remember the different version of this one by substituting sin squared with 1 minus cos squared. That's going to help us because if we substitute it in, everything will be in terms of cos of a single angle. So we would get 2 cos cubed x minus 1 minus cos x plus 2 is equal to 0. Expand it out. We get 6 cos, so that should be a square, 6 cos squared x minus 3 minus cos x plus 2 is equal to 0. Okay, collecting terms here, we've got 6 cos squared x, that's fine. We've got a negative cos x, and we've got negative 3 plus 2, which is negative 1. Okay, we've got a quadratic here in terms of cos x's. Can we factorise? Well, we can try. Let's try and put them into brackets as 3 cos x, 2 cos x. And let's put minus 1 here and plus 1 here, equals 0, and that factorises perfectly for us. So therefore, on the one hand, cos x is equal to negative 1/3 from this side, or over here, cos x is equal to 1/2. And therefore, x from this one is the inverse cos of negative 1/3. And from this one, x is the inverse cos of 1/2. Okay, and we use our calculator to work this one out. So we do inverse cos of negative 1/3, and it's giving me the answer x is equal to 109.5 degrees. And here, if we do the inverse cos of 1/2, we should know this one, but we get ourselves 60 degrees. So to find all the other solutions, as always, draw ourselves a cos graph here. So here's my cos graph to help. Let me just actually move that over here so it's not in the way of my future working. The cos graph goes down like this, up like this, like here. That's 90, that's 180, that's 270, and that's 360. And where is 109.5? Well, 109.5 is somewhere here. Okay, so that is 19.5 away from 90. So there'll be another answer here, which is 19.5 back from 270. And the other answer we would therefore get is 250.5 degrees. And this one here, we have an answer, we're looking for an answer of 60, which would be somewhere here, 60 from a peak. So the other answer will be 60 back from a peak, so it'd be at 300 degrees. And I'd encourage you to make sure you sub those values back into the equation just to check they all work. But in this case, they will all work, and you have found yourself your answer. Okay, time for you to have a go at one yourself, solving an equation using the double angle formulae. So here you go, pause the video, try this one out, and watch in 10 seconds as I go through. Okay, so your only option really was to use the double angle formula here. Again, rather than substituting cos squared minus sine squared, it will be easier for you to substitute 2 cos squared theta minus 1 in for this, because then everything will be in terms of single cos theta, and that will equal 1 minus cos theta. Subtract 1 off both sides and add add cos theta to both sides. You would get 2 cos squared theta plus cos theta minus 2 is equal to 0. A quadratic in terms of cos thetas here, you can attempt for a few minutes to factorize. You find out you're not able to, so you use the quadratic formula. The solution x is equal to negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. Okay, so we're going to use that for what cos theta is. So cos theta, with a is 2, b is 1, and c is negative 2, would be negative b, which would be negative 1, plus or minus the square root. B squared would be 1, subtract 4 times 2 times negative 2, and all of that divided by 4. And that would be equal to as follows: negative 1 plus or minus the square root. Well, this here would end up being root 17 over 4. So on the one hand, cos of theta would be minus 1 plus root 17 over 4. And on the other hand, cos theta would be minus 1 minus root 17 over 4. Now if we work those out, negative 1 plus the square root of 17 divided by 4, this would give me that, if I took inverse, that would give me that theta is something like 0.78077, etc. Cos theta is that, sorry. So theta would be the inverse cos of this, which would be equal to 38.7 degrees. This one over here, negative 1 subtract root 17 divided by 2. This here would give me a cos theta is equal to minus 2.56. You ignore this because cos theta can never be smaller than minus 1. Cos theta is always between 1 and minus 1. So these are where your only answers come from. Let's just check if there are any others. Draw yourself a cos graph. You're going between minus 180 and 180. So looking something like this. And you know 38.7 is an answer, which is here. So you know that by symmetry, negative 38.7 is also another answer. So your solution to this problem is that theta is equal to positive 38.7, and also that theta is equal to negative 38.7. And you're done. Okay, and then just to finish with, this topic's pretty much there now. I would encourage you to read chapter 7, page 113 to 120, and look at all the examples, and do in full exercise 7b and 7c. It's very important you get these identities in your head. They're going to be used throughout core 3 and in core 4. Thank you for watching.